Hello, everyone. So this talk is about Gaussian Lagrangian galaxy bias. So I think I should explain a few words here. So first of all, I guess all of us know what we mean with galaxy bias. So that is, this is like the universe, like we might observe it, right? Like the distribution of galaxies. And so this is this universe how we can easily model it. Like we can very well model gravity and run like dark matter only simulation. And galaxy bias is the connection between the two, and it's of course very important to get that right for doing cosmological analysis. And I think we already all got familiar with the like a statistical bias models and the EFT. So like in that approach, right, one treats gravity predictably. So that's the part we really put model. We know what we are doing, right? And so then we deal with the galaxies in a bit different way, in a statistical way. So we have this galaxy catalog, right, which is a set of points, and we coarse-grain the galaxies to define like a continuous galaxy density, and then so we assume the continuum limit, and then we expand the galaxy density perturbatively as a function of the matter distribution. And this formalism can also define something like a likelihood that tests the probability of observing a full galaxy density field given like the matter density field and maybe other properties like the tidal field or things like that. So also known as the EFT likelihood. So I just want to give it like a little bit of a spin here. So which I would call a bit a probabilistic perspective on this. So and like one thing that sometimes bothers me here a bit is that we have this additional coarse grading step. So like our observation, like we have this set of galaxy points, right? But then we coarse grain them to a continuous galaxy density. That's a discretization step, right? And maybe some cases we might be able to avoid that and instead try to kind of define a joint probability distribution over the locations of our galaxies. So I think that this is not something that I can do in this talk, but I think I can at least provide an idea how we can take some steps in that direction. And so of course if we did something like that, we would still want that this is kind of EFT consistent on large scales, but maybe also has some other nice properties so that we can really talk about probability densities, right? Because let's say we're in a regime where we made our cell size so small that we have like a 0.1 galaxies per cell or so. At that point, I think it makes more sense to talk about probabilities than continuous galaxy densities. So one word that I should explain a bit is the Lagrangian space. This is an illustration of Lagrangian space versus Eulerian space. So Lagrangian space is the space of the initial conditions. We start often like our simulations from a uniform grid, and then we put the perturbations, and we run the simulation, and we end up with this highly nonlinear distribution in our n-body simulation in Eulerian space. And so this is Lagrangian space. And you can imagine, for example, if I, let's say I mark the center point of this halo, right? So if I went back to the initial conditions, it might have come roughly from here, and you can see maybe this is the full Lagrangian region of the halo. And of course, there's a displacement between Lagrangian and Eulerian space. But one nice thing is you can unfold all of the structure into Lagrangian space and becomes a bit simpler to look at. So one additional nice aspect of going to Lagrangian space is that all of the initial statistics of the initial density field is Gaussian, right? So that makes, for example, very easy to define a prior on what is linear density and so on, and we have that right at hand when we're in Lagrangian space. And so if I talk about Lagrangian bias, right, then the goal is kind of to define galaxy formation as a functional that takes all these properties of the linear density field we might have available to predict whether a given Lagrangian location may form a galaxy or not. One really nice aspect of Lagrangian bias is that it naturally advects galaxies in a plausible manner. So I have this visualization I want to show you to give you a bit an idea of what that means. So in this case, you see like a visualization of an n-body simulation. So this is actually not a movie, but it's a drawn live right now. And so if I press this button, simulate, it will start the simulation from the initial conditions and run it live here. So you can see how structures are forming, creating halos and everything. So now, if I take so I've also built in like galaxies into this visualization. So they look like this. So each galaxy is just a point with some, light in the surrounding. And in this case, I'm using a Lagrangian bias model to define galaxies. So the way you can think about it is that I take in the initial conditions some points that I say this particle will become a galaxy at some point. And now, if I simulate this again from the beginning, you can see that also galaxies are forming over time and they're moving very naturally. They're following the flow of the matter, and you get a very plausible looking thing about the universe, right? And that's even with very, very simple statistics. So that's a Lagrangian bias model. So in this talk, I want to kind of define and measure this Lagrangian bias function in a general way. And I want to use kind of probability theory language to define that. So let's think of the following prediction problem, right? So we are somewhere in our Lagrangian space and we have available the linear density field, and we want to predict what is the probability of forming a galaxy in the center of this image at the cross, right? So we may have different types of information available, right? Either we have maybe the full linear density field available, like you might want to do in machine learning, or you could say, I only have something like the smooth version of the density field available, or only the local density, or like the tidal field, or the Laplacian of the density field. Could be any type of information. And so now if you know that information, it will change the probability that you should predict for whether this forms a galaxy or not. So I would phrase this as you have like a conditional probability. So if you have this information X, then you have a higher probability or a lower probability of forming a galaxy than this average probability. And that we can call a bias function. And so how do we measure that thing? There's a very simple related quantity that we could actually look at. So in this case, I've traced back a set of galaxies back to Lagrangian space. So the way it's done is just to the most bound particle also of a galaxy. Because in principle, they would have some extent, but I think it's negligible on this case. So in each of these points basically is some particle that I should tag as a galaxy in my model. Now, if I measure, for example, the linear density field at the location of every galaxy, so I will just make a histogram, you get this orange histogram distribution. You can see that it's different than if I randomly selected any point in the initial conditions, then I would get this blue histogram. That's this distribution at the location of random particles. I would call this the galaxy environment distribution because it describes the local environment of every galaxy that has formed, right? So now we can rearrange our probabilities a bit here. I'm not going to go through that, but so if you do that and you figure out that what I just called the bias function, I can easily measure by taking this orange histogram and dividing it by the blue histogram. Very simple, right? So I get this thing on the right side. And so you can see, that this function basically describes how much more likely is it from a galaxy if I know something about my linear density field, right? You can see if I know have a large density, then it's more likely from a galaxy. Low density is less likely. What you also see is if you have very small densities, it's not like you get negative probabilities or anything like that, but this probability just goes to 0. And so, yeah. Sorry? So what's my scale? I think this is maybe a smoothing scale of 0.2 or so, h over megaparsec, intermediate smoothing scale. So actually I looked at this for many different smoothing scales and also like halos, like different, or even for galaxy box. And I just checked this function for many cases. So for example, this is a very small damping scale, or KD, or like a large smoothing scale, right? You can see this bias function can be approximated well by many different methods, right? So you can put a linear bias model, or a quadratic bias model also works very well on that. Or this purple line is what I call a Gaussian bias model, and that fits, all of them fit quite well at that scale. So let's say I go a bit smaller scale, you can see this is, you can still approximate that well with different bias models, but somehow this function want to be very close to a Gaussian, which is the purple line. And I go an even smaller scale. I mean, now of course no one would expect anymore that you can fit this with a standard bias exponent, but the function still want to be a Gaussian. Or let's say I take stellar mass selected galaxies, also very much a Gaussian. Take star formation rate galaxies, star formation rate selected galaxies. So in this case, you can see there's actually not exactly a Gaussian anymore, right? But it's also not badly approximated by a Gaussian. So, I mean, so what you have to look, I mean, this plot may sometimes be a bit misleading, right? So you have this, like this, at this very high density, it's not well approximated by Gaussian, right? But if you weight it by how many volume elements you have in that regime, it is, right? So this is more maybe the distribution you would actually care about. So Gaussian seems like a very neat approximation to that. So we have here measured that through systematically. Just forget the right plot, just look at the left one. So here I look at the Wasserstein metric between this distribution I was showing on the left-hand side. If you approximate with a Gaussian or with a quadratic bias model. And so that metric, so the larger it is, the worse the model is. Reason I use this metric is because the quadratic bias model may predict you negative probabilities. So I cannot use standard probability metrics, but Wasserstein metric you can also even define for negative distributions. So Wasserstein metric is also known as Earth movers distance, that tells you how much you have to, on average, move probability around to recover the original distribution. So you see the bright lines are always a quadratic bias model that has the same number of parameters like a Gaussian bias model in dark, right? You can see it depends a lot on the tracers you're looking at, how well things work in a quadratic bias or not. So, for example, if you take 10 to the 15 solar mass halos, actually on almost no of these scales do you have a good approximation with a quadratic function. Whereas if you use a Gaussian bias, it's actually fine or across all the scales. Wasserstein metric even being 1 or 2 orders of magnitude smaller. So I've also checked this for a multivariate case. So when you take EFT, right, it tells you that you should not only include the Lagrangian density, but also the Laplacian of the density field and like the tidal field and other variables in your expansion. And so if you have now 2 variables, let's say density and Laplacian, and then you just get a multivariate Gaussian, very simple. So the parameter you have to look at is this one, right? That's the measured 2D bias function in this space. This is the Gaussian approximation, and the top right is the quadratic approximation. So seems the Lagrangian bias function of halos is always well approximated by a Gaussian, and this is even so, beyond the perturbative regime, apparently. The differences get the largest when you have the most extremely biased objects. But one might ask, and that's a very important question to answer, is if I fitted a Gaussian function on one smoothing scale, is that still valid on all larger smoothing scales that are larger than that scale I'm looking at? So one has to understand the scale dependence of this bias function. I already showed you that a bit before. Right here you can see if I measure this bias function at different smoothing scales, right, it changes shape because at different smoothing scales I have different degrees of information about the question whether I form a galaxy or not. So if you go through the math, if you come up with this formula, which tells you if you want to know the bias function at a larger smoothing scale, you have to convolve with the bias function at the smaller smoothing scale with the conditional probability of the small scale density given the large scale density contrast. That conditional probability is always a Gaussian in the linear density field. So what I'm basically saying is to get from the blue function to the to get from the red function to the blue function, well, not exactly this function, but the other function, I smooth with the Gaussian. So then one could even imagine doing this kind of smoothing scale relation up to infinite scales, and you can call that something like a renormalized bias function. So that's a large scale limit of a bias function. So if you do this with a Gaussian bias model, so let's say you write down at infinite scales that the logarithm of my bias function should be like a quadratic function like that. Then at finite scales, you would calculate this renormalized form of a Gaussian. So that's the same thing why you have in the bias expansion to sub delta squared minus sigma squared, right? And on the Gaussian level, it looks like this. But it basically tells you, if you smooth a Gaussian, with a Gaussian, you get a Gaussian again, right? So it's actually very simple. Just the normalization coefficients make this look a bit more complicated. And so then you can describe this bias function across across many different smoothing scales, right? So in this case, for example, I fitted the bias model at k of 0.2, right? And then I just take the same bias coefficients, but evaluate this function at different scales, and you can see that you recover exactly the scale dependence of that function. So one even can directly measure this large scale limit of the bias function at the finite scale. Can go through the statistics how that works, but you can see the large scale limit of the bias function as you would recover it by measuring at different scales, and you would always reconstruct the same bias function roughly, right? And that one also is consistent with the Gaussian. So why should the bias function be a Gaussian? I think there's no super fundamental reason, but there's a practical reason. So I already mentioned that if I have a small scale bias function and I want to see how it looks if I measure it on much larger scales, then I have to convolve with a Gaussian. So now if I take any of these functions you see up there, right, like I take a quadratic function, or I can take a top hat or triangle or delta function. If I take any of these functions and I convolve it with a much wider Gaussian, which I do if I look at larger scales, then I get a Gaussian function, or at least something that's quite close to a Gaussian. Right? It's not guaranteed that you get a Gaussian if you convolve with a Gaussian, but you can imagine that you tend to get a lot closer to a Gaussian if you do that. You can also see another example, for example, this green line, right? So that's been an error function on small scales, and on there has been a theta function on small scales, and on large scales you get an error function. Not exactly a Gaussian, still much better approximated by a Gaussian than by a quadratic function. So I just want to briefly mention how much? Just want to briefly mention that one can formalize a bit in such a form. So instead of writing the canonical expansion like we do with, I take my density and say it's 1 plus b1 delta and so on, you could write instead something like the logarithm of f is a polynomial expansion, and then you guarantee that it's a positive function, right, which has nice properties. And if you go through the math, actually you would argue that this would be something like the cumulant generating function, where the canonical expansion defines a moment generating function. And so you would then define different bias parameters that are somehow like the cumulants of this distribution instead of the moments of the distribution. And we know that in most cases you prefer cumulants to describe statistics rather than moments. I want to briefly mention so that actually if you take known results from the literature, like for example these coevolution relations for halos, very well measured by Tito and Lazaras in the separate universe simulation, and you just draw the cumulant combination of these bias parameters, then you get these beta 3. So this is B3, right? And you get beta 3 at third order, and it's completely predicted by B1 and B2, and it's 0. So this third cumulant is going to be 0. So saying the same thing in different words. So I'll leave you with that, I think.
Okay. Thanks.